Welcome to Graphing Rational Functions. Here are two examples of rational graphs. Notice in rational graphs there are often areas where the graph is broken up or discontinuous. And so that is why we have, like in this graph here, we have this piece of the curve and then there's a break in the graph where it continues here in this part of the graph, or here we actually have two discontinuous sections or discontinuous breaks. We have this piece of the graph here broken up, and then there's a break in the graph. Then we have another section here in the middle, and another break in the graph, and then here is the last piece of the rational function here. Because of the breaks in rational functions, there is a lot of conversation about end behaviors of the graph. End behaviors is basically talking about what is happening here in the graph at this end of the rational function, what's happening at this end of the graph for the rational function, what's happening at this end and this end. So when we talk about end behavior, we're talking about what's special about these values at the ends of the graph. And this is very important, and understanding the end behaviors is really what's going to help you graph the functions. We have already been having conversations in class about end behaviors, even though we have not been recognizing them as end behaviors. So an example of this is if we look at this denominator here, we already know that there's an excluded value for x, and that's -1. So because of the denominator x plus 1, we know that -1 is an excluded value. And if you look at the graph, this is the graph for this function here. When we look at -1, we actually see this red dotted line here. That's called an asymptote or a boundary, and that matches this value right here. And so you can see in this graph there's a break in the function to go from here to here. So this here is a boundary, or what we are actually going to call an asymptote. We're going to take a minute coming up here to define these special terms here with the asymptotes and boundaries in a minute. But here's another example of where we have some excluded values here based on the denominator. We know that x cannot equal 2 and x cannot equal, -2 and -3. And so we know that on the graph, -3 here is a special value where the graph is going to have a break. But at -2, we actually have what is called a hole in the graph instead of a boundary. And that is because when you go back to the rational function here, we actually see that this x value here actually cancels out because the numerator also has the same factor, x plus 2. So in this special case, because the factors x plus 2 cancel out, this excluded value ends up being a hole rather than an actual vertical boundary. Those are special cases. So to sum it up, the important parts here is for the denominator, it's going to have great importance on identifying your vertical boundary. Those are always going to be your excluded values, which are the same excluded values we've been finding earlier in this unit. Going back quickly and reviewing the other end behavior, horizontally, we have some interesting things happening here at the ends of the graph as they're leveling out horizontally. So what is happening out here in the negative x direction, the negative domain, as this graph is approaching very big negative x values, there's like a leveling off behavior that's happening here, but it will not cross a certain value here. And same thing in the positive domain. So out here in the big positive x values, the graph is going to approach the same value as this side, but from the other direction. So from underneath, it's approaching the same value here, the same y value. So this happens as big x values are put into the function. It'll approach the same y value, but from different sides of the y value. So in summary, when we're trying to find our horizontal end behaviors, we are going to put in or evaluate the function with really big x values. So here is the overall process we're going to use to sketch our rational graphs. So first step will be to factor both the numerator and denominator. Then we'll want to identify the excluded values based on the denominator. We're going to want to reduce or cancel any factors on the top and the bottom that are the same, if possible, so this doesn't happen too often, but it could. If we have any canceling factors, these are going to be your wholes, and you're going to want to keep those in mind and maybe label them as wholes on paper. Your vertical asymptotes are going to be whatever factors remain uncancelled still in the denominator. So these are going to be your dotted vertical lines that you're going to sketch in your picture. Step 6 are your horizontal asymptotes. You're going to have to evaluate the function by putting in big values for x. I usually just put in some big positive values because it's going to tell you the same thing if you put in negative values, so it's easier to work with positives. And I evaluate both 100 and 1,000 just to investigate the y value that the function is approaching. Step 7 is going to be making sure you're sketching your asymptotes or your vertical and horizontal boundaries. And then you're going to want to make a quick XY table to pick an x value on each side of the vertical asymptotes, substitute them in to your reduced function. So this is the function that you get earlier from after step 3. You're going to finish the graph by plotting the points you get from your table in step 8 and just putting in the functions with the curves. Here's the first example we'll take a look at. First thing would be to factor the numerator in the denominator. X plus 1 is already a prime value since we don't see any x squares or GCF values that can be factored out. Same thing on the bottom, x plus 3 is already prime. So in this case there's nothing to factor. The next step would be to identify the excluded values for the denominator. So x plus 3 is going to tell us that we do have an excluded value at x equals -3. So we know that on the graph it will be discontinuous at the value of -3 for x. The next step would be to cancel factors top and bottom if there's anything to cancel. In this case there is none. So the function remains the way it looks like, and we now know officially that x equals -3 is a vertical asymptote, which means it's a vertical boundary at that value. Now our job is to find what's happening for end behaviors horizontally. So to do that, we actually have to investigate what is happening at the ends of the graph, and this is where I'm having us substitute a couple big values for x. So if you plug in 100 into the function, both on the numerator and denominator, and simplify, that'll give you a general idea as to what values the graph is approaching. So 101 divided by 103 comes out to 0.9805. Now we investigate how that changes or not with even a bigger value like 1,000. 1001 divided by 1003. So with 1,000 for x, the y value now is 0.998, which is a tiny bit closer to a certain value that I'm going to call 1. So here I believe that the horizontal boundary is going to be at y equals 1. Basically, you got to take your decimal values and round, look at what's happening to the pattern with the value, round it to the closest value you think it's approaching. So at this point, we actually can sketch our two boundaries. I'm going to call this the horizontal boundary or horizontal asymptote, y equals 1. And those will go in the graph, positive 1 on y. And for the vertical asymptote, it's at negative 3 on x. And so now you can sort of get a general picture of what our graph's going to look like. We need to now figure out where's the actual function sitting. Is it sitting above or below? Above here or below? So this is the step where we got to make a small little table and pick an x on this side of the vertical line and a different x on this side and plug it into our function. Two values I'm going to pick for y, and you can pick any values you want. I'm going to pick negative 4 for my table and negative 2, and I'm going to plug those in and find what the y values are going to be, and that's going to tell me the point on the graph where the function is going to cross. So plugging in negative 4 is going to give me negative 3 on the numerator, negative 1 on the denominator, which is positive 3. Plugging in negative 2 is going to give me negative 1 over 1, which is negative 1. And so now I have 2 points I can plot on my graph. Negative 4 up 3 is over here, and that tells me my graph must cross that point. So it's on this side, or this side of the two boundaries. Negative 2, negative 1 is down here underneath the horizontal. So that tells me that this other part of the graph is underneath down here. And again, you just do your best. This is really a rough sketch, but you got to try to have a rounded corner here as best as you can. Try to go through your point, and same thing here. This one looks not too nice, but it's just a rough sketch with your boundaries and your graph.